Hi there. I have to be gone today, and so ideally you have checked in with the sub and you have received a piece of paper that at the top says Newton's first Ewish. If not, then please pause this and get those papers passed out, and we'll get started. Today we are going to learn all about our first physics hero, Isaac Newton. Isaac Newton was a very important guy as far as physics is concerned. Newton was a major nerd. He lived about 350 years ago, but we haven't improved much on what he thought, which is pretty amazing if you consider how much science has changed in the last 350 years. Most of what we now call physics he discovered. In fact, he figured out so many things that contemporary scientists of his time complained that there was nothing left to be discovered after Newton came along. When his math got complicated, he invented his own simplified version that we call calculus. If you think calculus is hard, you imagine the math that it replaced. It actually made it quite a bit simpler. So calculus was something that Newton came up with to make his math a little bit simpler. His teacher was a guy named Galileo Galilei. I don't know why his mother would do that to him, but he was the guy who came up with all those formulas that we learned last week. Galileo did. And he also took the telescope from a toy and turned it into an actual scientific optical instrument. And so this was the guy that Newton got to learn under. Newton ended up developing all the optical formulas that we will learn in Unit 11 and the concept of universal gravitation that we'll cover in Unit 6. But what's cool is that not all the things that Newton came up with, but the fact that even though he did come up with all this stuff, he didn't think he was all that. He gave credit to others for his ideas. He said, "If I have seen farther than most, it is because I have stood on the shoulders of giants." So he considered all the people who came before him to be the giants, and he just happened to come along at the right time, and he was able to see some patterns that other people didn't see ahead of time. Most importantly for this unit, Newton came up with 3 Ewishes. Now, others came up with important details, and many of these parts were well known, but like I said, Newton came along at the right time, and what he did was he took what seems to be really complicated motion, and he broke it down into 3 simple rules. These are often called Newton's 3 laws of motion, but we do not like that phrase. No, no, no. The reason we don't like that phrase is because laws sound immutable and concrete, and science should always have the attitude that this is the best model we have now. If something better comes along, then we will throw away the old model and we will adapt the new model. Of course, scientists, being people, are oftentimes hyperly committed to certain ideas, and so some ideas stick around even though we have a lot of good information that says this isn't the best idea, but people say, no, but this is my idea. But that's not what we should have. We should have the attitude that this is the best model, and when we get a better model, we throw out the old model and we adapt the new model to it. But we don't do that always. So in our class, we will always have that attitude, though, and to show that proper attitude, we are going to call them not Newton's laws, but Newton's extremely well-supported hypotheses. If you look at the first letters there, E-W-S-H, that's where Ewish comes from. So Newton's Ewishes are his extremely well-supported hypotheses. And since no one has improved on them in the last couple centuries, other than minor tinkering in weird circumstances, they are indeed extremely well-supported. When do they not work? Pretty much it's like, oh, I happen to be going at 90% of the speed of light one direction, and you're going at 95% of the speed of light the other direction, and you pass each other on the highway, and the speed that you pass each other at is not the speed you expect it to happen. But since most of us don't drive close to the speed of light too often, this doesn't really happen to be something very important in your life. So anyway, there are 3 Ewishes that we need to understand. The first Ewish, of course, is called Newton's first Ewish. His first Ewish says an object in motion tends to stay in its present state of motion in a straight line unless acted upon by an unbalanced force. Isn't that beautiful? That's nice book language. I like to rewrite that as objects like to keep doing what they've been doing. In other words, inertia. You should have learned about inertia reading the notes that I handed to you after the test. Inertia, of course, is the Greek word that means laziness. And so inertia means I like to keep doing what I've been doing. If I'm not moving, I want to stay not moving. Once I'm moving, I want to keep moving at a constant speed in a straight line, that sort of thing. So I use that. So, and now a word from our sponsor. We're going to pause right now for a second because there are 3 Latin phrases that every educated person should know. If you don't know these phrases, then you're just going to look foolish when you get to college. I don't want this to happen. So the first one is the one that I just used, i.e. I.e. does not stand for in example. It stands for the Latin phrase id est. The Latin phrase id est literally means that is. So you would use that whenever you are rephrasing something. E.g. is what we use when we have an example. This actually stands for the Latin phrase exemplari gratia, which means a free example. The third one is etc., which a lot of people think that's one word, but it's actually 2 words. It's etc., which literally means and the rest. So the top one, i.e., you use i.e. whenever you are rephrasing something. So if I have a definition that I want to rephrase, I would write i.e., and then I'm going to use it in different words like I just did. E.g. is what we use when we want to give an example. So do not use i.e. when you want to use an example. You will just look foolish. Etc. Of course, most people use right, but it's just more fun to write it out because it's prettier in 2 words. So now we go back to our regularly scheduled programming already in session. So if you'll notice here, we have Newton's first English in book form, and then i.e. I rephrase it as objects like to keep doing what they've been doing. I haven't given you an example there. I just rephrased it in a different manner. So there's a couple conditions that you need to note. It says an object in motion tends to stay in its present state of motion in a straight line unless acted upon by an unbalanced force. So if an unbalanced force acts on me, then Newton's first law is off. It doesn't work anymore. So that means it only works when our forces are balanced. When our forces are balanced, that means they are either equal but opposite, or they're absent entirely. And so if our forces are balanced, then our motion is always going to be at a constant speed in a straight line. So my forces are balanced. The only motion I can get is constant speed motion in a straight line. So by now you should have those first few blanks filled in. If you don't have those first few blanks filled in because you were all mesmerized at the sound of my voice, but you weren't actually looking at your paper, fill those in now in case you may need to pause this. Now we'll give you some examples of Newton's first English so that this gives you a kind of good graphic example in your head that you can remember. If you've ever been sitting in your car at a red light and the car turns green and suddenly you floor it, what happens to your head? Well, of course, you're thinking my head goes flying backwards, but your head does not, in fact, go flying backwards. What happens was when you were sitting at the red light, you want to not move because that's what you're doing. So your body wants to stay not moving. Now, when you floor it, your car starts shoving itself forward, and as it's going forward, your car's accelerating forward, but your body wants to stay where it is. Well, your body is pretty well tied into the car because you're sitting in the seat, and so the back of the seat shoves you, but the part of your body that's least attached to the car is your head. So your head tries to stay where it is, even though your body's being shoved forward. Your head is like, no, I want to stay back where I used to was. And that's why it feels like it's going backwards. It's actually just trying to stay where it used to be. On the other hand, if I slam on the brakes, what happens is I used to be going down the street at 20 miles an hour, and I want to continue to go down the street at 20 miles an hour, but when I slam on the brakes, then suddenly my head says, no, I want to keep going 20 miles an hour. Of course, you slow down because you are locked into your car with your, not seatbelt, but inertial restraint. Your inertial restraint restrains your inertia. So next time you're in the car with your mother, say, are you wearing your inertial restraint? And she'll say, that's none of your business, because she doesn't know what you're talking about. But anyway, your body is going to slow down with the car because you're tied to the car with your inertial restraint, but your head, being less attached to the car, wants to keep doing what it's been doing, so your head feels like it's flying forward because it really is flying forward. Icy roads. Now, I realize that we don't deal with ice too well here in Laredo. On the one time every 3 years, there's a threat of ice. We, of course, cancel school and everything goes crazy. And so that doesn't happen a whole lot. But up north, it actually happens periodically that you get ice on roads. And when ice gets on roads, you will find that friction goes away. We will learn about friction more tomorrow. But when friction goes away, Newton's first e-wish takes over. The only thing we can do is move at a constant speed in a straight line. And so you can't stop, you can't turn, you can't change speeds, you can't change directions. It gets really kind of nerve-wracking. There was one time where my wife and I were driving home from visiting relatives up in the Great White North in the winter. It was over Christmas break. And we were coming back home. This was when our first child was about 4 months old. And it was my wife's turn to drive. And we were driving through Oklahoma City on the way back to Laredo. And it had been snowing, which hit the ground and melted. But the sun went down. And once the sun went down, all that wet stuff that used to be on the road turned into ice. And so she pretty soon was driving on ice. As she's driving on ice, she turned to me and said, well, what should I do? And I said, well, what you want to do is just not change your motion. You don't want to speed up. You don't want to slow down. You just want to keep doing what you've been doing. That worked out really well for a little while. After a while, though, all of a sudden, the car started to turn ever so slightly. And so, she grew up knowing how to drive on ice and snow, and so she turns out of it. But when she turned out of it, she started going too fast the other direction. So then she turned the other direction, started going even faster the other direction, and then she started going the other direction. And every time she corrected, it got worse the other way. Before you know it, after 4 or 5 corrections, we were actually spinning around. At that point, she starts to panic. I told her, you want to do 3 things. Number 1, take your hands off the steering wheel. Number 2, take your feet off the pedals. And number 3, relax. Well, she did the first 2. As we're sitting there spinning around slowly as we're driving down the road, she was hyperventilating, but I was nice and calm. The reason for this is she had never taken physics, but I kind of know physics a little bit, and I knew that if we have nothing but ice, which is all we had seen for quite a while, that my only motion is going to be constant speed straight line motion. I know that the fact that we're spinning shouldn't matter at all. We're going to continue to go down this nice level straight road at a constant speed in a straight line. Of course, air resistance is going to slow us down, which it did. So after spinning around 10 or 12 times, we finally came to a rest on the side of the road, and she jumped out and said, "You drive." So I got to take over driving. In the trunk of your car, you have a thing called a jack. This jack is useful for lifting up your car. Now, when I was a kid, your spare tire and your jack just kind of bounced around in your trunk, and that's the way things were. You got groceries, you had to kind of shove those over to the side, and you stuck your groceries in there, and they just bounced around in the car. But now, if you go inside your car, there's a special spot for your tire, and your tire fits in a little spot, and underneath the tire, the jack fits in, and the jack kind of locks in place, and it's bolted down. Why are things the way they are now compared to the way they were when I was a kid? Well, car manufacturers found out a very important thing. If you get in a wreck and you die in that wreck, you never buy a new car. So they started thinking, hey, if I keep you alive in a wreck, then your old car is trashed and you're in the market for a new car, and I can sell you my new model. So this was the important discovery that they came up with. What was happening was, say you're going down the road at 40 miles an hour. Back in my day, you're going down the road at 40 miles an hour and suddenly this tree jumps out in front of you. Wham! You hit the tree, you stop. You have no trouble stopping because you are wearing your inertial restraint, but your jack in your trunk wants to keep going 40 miles an hour. So now you have this large chunk of metal that's flying at the back of your seat at 40 miles an hour. Of course, the back of your seat slows it all the way down to 33 miles an hour, where it hits you in the back of the head. So if you have this large chunk of metal that's flying out of the trunk and killing people, the guys started thinking, you know what, maybe it's not just the people that need a seatbelt, but also the jack. So now your jack has a spot that's locked in, and your spare tire has a spot that's locked into your trunk, so that they have their own inertial restraint, so that when you have to stop in an emergency, they don't jump out and kill you. The reason I bring this up is that some of you change a tire, and you're tired and cranky when you're done changing the tire, and you just toss this stuff into your back of your trunk, and you say, later I'm going to put it away. And of course, later has been already a month and a half and it's still bouncing around in your trunk. I want you to make sure that that is actually put away properly, because I don't want you to die just for fun. Anyway, ice and drinks. Have you ever been somewhere where there's this annoying chunk of ice and it's sitting in your drink and it's like in the way and it won't go away, and you've spun your cup but the ice chunk stays right there? What you have to do is outsmart your ice. So if you hold onto your cup but you walk to the other side, then the ice will be on the other side. You'll have to try it next time. Back in the day when we used to listen to CDs, you used to put CDs on the dash, and when you had CDs on the dash, what happens is you're going down the road and everything's wonderful until you make a sharp turn. When you make a sharp turn, you'll notice that the CDs start sliding off to the side. Now, if you make a sharp left turn and your right window happens to be open, you will find that the CDs just go flying straight out. So what you find is that CDs come flying out of cars at intersections. Back in the day, we used to use cassette tapes, and they would always fly out at intersections, and you'd always see this cassette tape that's been run over 10 times, and you've got this little streamer going all the way down the street. And it was always at an intersection that you would see these. What's really happening is your CD is not suddenly sliding to the right or sliding to the left. It's actually trying to still go straight. So if you imagine your car, if your car is going straight, everything in your car wants to keep going straight. But if you suddenly turn to the left, then what is in the straight direction before is now the right side of the car, which is why your body slams over to the right when you're turning a left corner too fast. But everything on the dash wants to go straight out that window because it's still trying to go straight the direction it was going before. If we take your car and we put it on the interstate, well, when your car is on the interstate, we tend to travel at a constant speed in a straight line. And again, Newton's first e-wish says, if we're traveling at a constant speed in a straight line, then our forces must be balanced. So if we're traveling at a constant speed in a straight line on the interstate, that means really the only forces that are fighting, the only reason that your engine has to keep pushing forward is to fight air resistance. If we had no air resistance, what we should be able to do is just cruise up to our cruising altitude, shut our car off, and then turn it on again when we need to change directions, 1,000 miles down the road. That'd be great. We'd get enormous mileage, but that's not going to happen because we have air resistance pushing back. So the whole reason we have to push forward when we're on the interstate is simply to fight air resistance. So if you want to get better gas mileage, it doesn't really matter what size your car is. All you have to do is say, I want to have more aerodynamics, because if I have better aerodynamics, then the air pushes less hard back, and so I have to push less hard forward to keep going. 18-wheelers, if you've ever been behind the tractor when the trailer is not attached, you'll notice that they have a piece of plastic that's attached to the top that's just hollow inside. And all it is kind of curvy. And what that does is it deflects the air over the back of the trailer rather than hitting that nice flat part at the front of the trailer. And so that little piece of plastic really helps their aerodynamics. And so that helps them get better gas mileage. Without that piece of plastic, they get like 8 miles to the gallon. With that piece of plastic, they get like 10 miles to the gallon. And you're thinking, well, that's only 2 miles to the gallon. Is that really big a difference? Well, yeah, if you go from 8 miles per gallon to 10 miles per gallon, that's like a 20% increase. That saves you 20% of your fuel cost, which is their main cost when they're driving. So that makes a big deal. Our last example are pigs in space. And of course, we're not really talking about pigs in space because we don't throw those too much. But if you watch The Muppet Show, there was this thing on pig. Never mind. Anyway, when you are in space, there is no air resistance. So like the cars on the interstate, like I said, we would get great gas mileage if there was no air resistance. Well, in space, there is no air resistance. So if I'm traveling to the moon, like astronauts did back when I was a little kid, what happened was there's not enough fuel to keep pushing that whole time, but you don't need to keep pushing. All you need to do is get enough fuel to get up out of our atmosphere and point in the direction that the moon will be in a couple days, and then you shut the engines off. And for the next 3 days, they traveled at a constant speed in a straight line toward where they were going. Then they had to fire up the rockets again to put themselves into orbit around the moon. But while you're traveling in space, once you get up to your cruising speed, you just shut everything off. And Newton's first e-wish, which isn't lying, it's going to keep traveling at a constant speed in a straight line. So again, Newton's first e-wish says, if our forces are balanced, we're going to continue to travel at a constant speed in a straight line. That's our main important. Now, Newton's first e-wish said unless, which leads us into the second one. What happens if our forces are unbalanced? If we do have that unbalanced force, we get into Newton's second e-wish. Now, Newton's second e-wish tells us that an unbalanced force is going to produce an acceleration that's directly proportional and in the same direction to the force, but inversely proportional to the mass. Isn't that beautiful? In formula form, we say the acceleration is directly proportional to the force, so the F is on the top, but inversely proportional to the mass, so the mass is on the bottom. Most of the time we move that M up next to the A, doing the algebra correctly, and we end up with F equals ma. This is the most important formula in all of physics. So, there are some new terms here. Now, if we look at Newton's second e-wish carefully, we say basically an unbalanced force is going to produce the acceleration, the unbalanced force. So if we have, what's a balanced force? Well, if somebody's pulling you with 100 newtons to the right and somebody else pulls you with 100 newtons to the left, that's balanced. Those are equal but opposite. But if somebody's pulling you 150 to the right and somebody else is only pulling you 100 to the left, then the unbalanced portion is 50 to the right. That's all it is. That's all unbalanced is figuring out who wins and by how much, what's left over. That's the unbalanced part. Well, that unbalanced part is going to produce an acceleration. You're going to get faster and faster and faster. We've talked about accelerations last week. So the unbalanced force produces an acceleration that's directly proportional and in the same direction to the force, which means if I give you a little push, you get a little acceleration. If I give you a massive push, you get a massive acceleration. It's directly proportional. And of course, in the same direction. If I shove you toward the north, then your body accelerates toward the north. It doesn't suddenly accelerate east. That would be pretty weird. So you accelerate in the direction I've shoved you. But what if you're already moving? Well, if you're moving toward me and I push against your motion, then I give you a negative force, which gives you a negative acceleration, and it will slow you down. So it's still in that same direction. The third part was it's inversely proportional to the mass, which means if I have a small mass, I get a big acceleration. If I have a big mass, I get a small acceleration. If I'm going to play soccer, I kick a soccer ball, which is a good sized ball, but it's filled with air, which means the mass is fairly small. Bob, our bowling ball, is about the same size as a soccer ball, but you would not want to play soccer with Bob, because when you try and kick that big of a mass, it would say, no, if I have a big mass, I want a tiny acceleration, and your foot is trying to cause a big acceleration, and so your foot would have to say, no, because Bob would say, I'm not going to accelerate that fast. And so then your foot would have to slow down a lot and you'd break your foot. So Bob would not be fun to play soccer with. So our new terms are force, mass, and acceleration. Of course, last week we learned all about accelerations, and we know the unit to look for is meters per second squared. When we see that little squared, we think acceleration. That one's no problem. Mass, on the other hand, is a new concept here. Mass is the amount of stuff in an object, the amount of matter in an object. So the amount of matter is also the amount of inertia in something. So if you have a small mass, you have small inertia. If you have a large mass, you have more inertia. Big people have more inertia than little people do. Little people are easier to knock to the side. So your mass always is going to have the unit of either gram or kilogram. Since grams are very tiny, the standard unit of mass is a kilogram. A kilogram in English units is about 2.2 pounds. Just to get it in your head, that's about a kilogram. So kilograms are what we're going to look for. So every time we see kilograms, we think mass, just like every time we see meters per second squared, we think acceleration. Force is new. We learned on the note sheet that a force is anything that pushes or pulls. It's very simple. Anything that's shoving on you, whether it's pushing or pulling, that's going to be a force. Well, the unit that's going to work with force comes from our formula. So our formula, of course, is F equals ma, Well, the unit for m was kilograms, and the unit for a was meters per second squared. So if I multiply a kilogram times a meter per second squared, I'm going to get a kilogram meter per second squared. That makes perfect sense. But of course that's too long, and so we abbreviate that capital N, which of course stands for Newton, our hero of the day. So anytime you see a Newton, you think, hey, a Newton is really a kilogram meter per second squared, which means if I take a Newton and I divide by a kilogram, what's left over is a meter per second squared. If I take a Newton and I divide by a meter per second squared, what's left over is a kilogram. So now let's try a problem. You have this written down for you already, except you have a different name. Deal with it. Jackie shoves an 8.67 kilogram box across the floor, accelerating it to 2.93 meters per second over a 14-meter displacement. How hard was she pushing? Well, again, with word problems, what we want to write down is what we know. So the first number we see is 8.67 kilograms. When you see kilograms, you of course instantly think mass. Then we have 2.93 meters per second, and when we see meters per second, we instantly think velocity, and then we stop and look and say, is this initial or is this final? Well, Jackie's shoving the box across the floor, accelerating it to 2.93 meters per second. So I say, hey, it got to this speed, it must have come from another speed, so this must be my final speed. Our third number says 14 meters, and anytime we see we think duh, so that's going to be a displacement. And of course, do we know anything that's not specifically written down? Sure, we know that our V initial here has to be 0 because boxes pretty much just sit there until you come along and shove on them. So that's going to be our initial velocity for the box. Now, how hard is she pushing? What are we looking for? Well, if she's pushing, any push or a pull, of course, is a force. So we're looking for force. So far, the only equation that we know about that deals with force is the one we just learned, F equals ma. Now, we know the m, that's the 8.67, but we do not know the a. But we know how to get a from last unit. Last unit, we learned how to find a from all kinds of stuff. This time, we have to say, well, which formula has a in it that also has the VF, the D, and the VI that I know already from what we know. So what formula has A and VF and VI and D in it? That, of course, was the last formula that we learned last week. VF squared equals VI squared plus 2AD, which after algebra is going to look like this. So that's going to be our A formula. Now, if we plug in all of our numbers, I'll give you a second to write that down. But if we plug in all of our numbers, and what's going to happen is we're going to have 2.93 squared minus 0 squared divided by 2 divided by 14. So again, if you're using fraction mode, no problem, make it look exactly like it looks. But if you're using your calculator in the regular mode, then divide by 2, divide by 14, because there's two numbers underneath, the way we did it before. After plugging that into your calculator, ideally you shove it into the person's face across from you and you say, did you get that? And the that you should have gotten is this. So that's our A. But of course we're trying to plug into F equals ma. We already knew the m, we didn't know the a. Now that we do know the a, we just plug in our 8.67, which we knew was the m, times the a that we just figured out, and that gives us a grand total of 2.658252964, and then we round. Now if we go back, we look at our formula, we say, hey, 8.67 and 14.0 and 2.93 all had 3 sig figs, so this answer should round off to 2.66 newtons. So yay team. Now remember, last unit doesn't disappear, we're adding to it. So you still need to be able to use those formulas we used before. We're going to continue to use those formulas for a long time, so make sure you're comfortable with all of those. Now we're going to switch to Newton's third E-wish. This is the one that most people have heard of, but most people misunderstand. Newton's third E-wish says that every action force has an equal but opposite reaction force. Most people have heard of this one before, but usually when you hear this one, you hear every action has an equal but opposite reaction. And you start thinking, hey, I flirted with that pretty girl, but she slapped me. That was the action, that was the reaction. That's not what we're talking about here. The most important word here, of course, is the one that gets left off when people talk about it, and that is the word force. This is all about forces again. So every action force has an equal but opposite reaction force. That means that pushes always come in pairs. Anytime I shove on you, you shove back on me. So there's a couple conditions to note. The pushes are paired, but they're acting on different objects. If I smack you in the face, your face smacks my hand just as hard as my hand smacks your face. Both forces are not acting on one object. My hand is acting on your face is acting on my hand. So what happens is when I smack you in the face, your head starts to accelerate in the direction that I shove you. That's back to Newton's second e-wish. But what happens to my hand? Well, my hand doesn't continue to move the same speed it was moving before. Once it interacts with your face starts to slow down my hand. If that slows down my hand, that means there must have been a negative force happening on my hand. And so that's what happens. You have to notice that the paired force pushes oppositely. I accelerated your head one direction, your head slowed down my hand, which means that was a negative acceleration on my hand. And so this is going to happen that direction. You see the same thing happening when little kids are playing t-ball. When you have a little kid that plays t-ball, if he misses the ball, what happens is the bat's inertia will make him swing around because he's a little kid and that bat's really heavy. But if he makes contact with the ball, he doesn't spin around. Because when he makes contact with the ball sped up from the bat, but the ball also hit the bat just as hard as the bat hit the ball. If the ball hits the bat, that slows down the bat and the kid doesn't spin around. If you've never been playing t-ball, probably at some point you've been in water. When you are swimming, it doesn't matter what stroke you're using, in all strokes, you're grabbing water and you're shoving it. But what direction are you shoving the water? If you've been swimming before, you know that every stroke you have, you're grabbing water and you're shoving it backwards. By shoving that water backwards, the water ends up shoving you forwards, and that's how you go swimming. Same thing happens if you're in a boat. You stick the paddle in the water and you shove the water backwards, and that shoves your boat forward. So that happens a lot. Another great example is jumping. If you've ever jumped before, you are shoving down on the ground and the ground is pushing you up. So is it fair that the ground shoves up harder on Michael Jordan than it does on me? Because he's got better hops than I do. So is that fair? Well, it comes down to Newton's third E, which says every force has an equal but opposite force. He pushes down harder than I do because his thighs are bigger than mine are. So if he shoves down harder, then the ground pushes up harder. Now, you notice that you go up, and of course the only way you can go up is if a force is shoving up on you, which is coming from the ground, so the ground is pushing up on you. But you are pushing down on the ground. Now, are you really moving the ground? The answer is yes. But the ground has a huge mass and you have a tiny mass, so you notice that you go up in the air, but you don't notice that the ground actually accelerates downward because, you're trying to accelerate the entire planet, so that doesn't work too much. But the question always comes up, what if? Yeah, what if? Well, what if everybody on the Earth jumped at the same time? Would the Earth go careening off its path and plunge into the sun? So this is always the big question that we have. Well, of course, the Earth is round, and if we're jumping and people in China are jumping, then we're pushing against each other, and that's not going to work too well. So we have to invite the entire world over to my backyard for a jumping party. So if we're all jumping in the same direction, again, according to Newton's third, this is Newton's third in formula form, every force has an equal but opposite force, F equals negative F. That should make sense to you. But again, we learned in Newton's second e-wish that F equals ma. So if I replace the F with an ma, then I have every ma has an equal but opposite ma. So what we have to do is figure out, well, how many people are on the Earth? Well, let's give a very conservative estimate and say that there's 7 billion people on the Earth, and we're going to average their mass out at 68 kilograms. That's about 135 pounds. Now you're saying, Paulson, I've seen a lot of people that are heavier than 135 pounds. Yes, but 75% of the world's population is under the age of 12, and really you don't have that many 6-year-olds that are 135 pounds. So we're just averaging this out again. So the total mass of humanity should be somewhere around 4.76 exponent 11 kilograms total. That's probably conservative, but you know, it'll work. Now, let's say our average acceleration is 81 meters per second squared. So that gives us a nice, good jumping ability. I know grandma can't jump too well, and none of the 2-year-olds jump too well. They only get 1 foot off the ground at a time. But we're going to average this out because we got some athletes out there too. Now, we have to know the other mass. The other mass is the Earth's mass, which everybody knows is 5.98 times 10 to the 24th kilograms, give or take a couple kilograms. So if we have our acceleration formula, if ma equals negative ma, then we have to move the Earth's mass underneath to find the Earth's acceleration. So on top we have the total mass of humanity and the acceleration of humanity, and we divide that by the mass of the Earth, and we find that that answer is 6.4 exponent negative 12, or to put that in normal numbers, it would look like that. So if this is the acceleration, everybody in the world comes over to my backyard for a jumping party, and we all leap up in the ground, off the ground at the same time, but you hang back just to feel it. That's the acceleration you're going to feel. Are you going to notice that? No. We're like a flea on the back of a dog. When it jumps off, the dog doesn't say, "Oh, I lost some weight." It's not going to happen. So the Earth is huge, and we're just a tiny little speck on it, and we're not going to do much. So that's about it. Here's a little video that one of my students gave me one time that demonstrates Newton's third wish, because another good example of Newton's third wish is a gun. When the gun shoots the bullet forward, the bullet shoots the gun backwards. If you've ever shot a gun before, you know this. This is a little scrawny girl shooting a 12 gauge for the first time. So you'll notice that her body was shoved backwards because it was shoving the little pellets forward. So again, that's another good example of Newton's third wish in action. To sum up, I can't do this demonstration because I'm not here to demonstrate it, so we'll have to try it another time. Your car's mileage. Once I had a small car that I traded in for a newer, larger car that happened to be more aerodynamic. Well, what happens to my in-town mileage? Well, in town, what happens is I'm speeding up, I'm slowing down, I'm speeding up, I'm slowing down. There's a stoplight, green light, red light, green light, red light. I'm constantly speeding up, slowing down. So here what comes into factor is Newton's second wish. Newton's second wish, again, F equals ma. So if F equals ma, then that means if I have a small car, small mass, I get a big acceleration from. So I don't need as much gas to accelerate a smaller car. When I switch to that larger car, now I have more mass to push around. It's harder. I need a bigger force to cause that same acceleration. So what happened is my in-town mileage actually went down. It was not as good. On the other hand, what happens to my interstate mileage? Well, on the interstate, then I'm traveling at a constant speed in a straight line, and Newton's first wish is the only thing that really matters. So if Newton's first wish is the only thing that really matters, then all that matters is how aerodynamic I am. So my new car, even though it was larger, was more aerodynamic than my smaller car was. So what happened was my interstate mileage actually went up. I got better mileage on the interstate with a larger car than I did with a smaller car. If we apply this to football, it's the same thing. The purpose of a lineman, of course, is to block, which means they want to not move. If you want to not move, then you want to be very large, because the more mass you have, the harder it is to change the motion of that mass. You have more inertia with that more mass. And so when you look out on the football field, the biggest guys out there, the guys with the most mass, are always linemen. On the other hand, running backs, they want to accelerate. They want to be able to change direction very fast. They want to be able to speed up and slow down very fast. And so they want to accelerate. So the size that's going to work best for them are going to be small. So typically one of the smallest guys on the football field is the running back. They're little guys, but they are able to accelerate more. Again, big mass, small acceleration, small mass, big acceleration. Get it? Got it? Good. So hopefully you've got this down pretty well now, and you are going to be ready. Your homework, of course, is to do problems A. Once you got problems A made, you got it made. So that should be easy. Make sure that you get a Unit 3 problem sheet from the substitute and go ahead and work in small groups on problems A. And I'll see you tomorrow.